Okay, good morning, everybody. Afternoon, evening, wherever you might be in the world. Thank you all for joining us today. Very excited for the second day of the virtual workshop on double categories. Slight name change from last time. And we're starting off today with our first talk by Nima Rasekh, who's going to be speaking on double categories in univalent foundations. So please, Nima, start whenever you're ready.
All right. Well, before I start, let me thank the organizers for putting this event together and bringing us all here online, and for like smooth organization and for inviting me. And yeah, before I also go into the talk, everything I say that will be new is joint work with, I think, Niels van der Weide, who is here, I think, and Benedikt, Ahrens, and Paige North. All right, so the aim of the talk is to talk about double categories. Well, it's a conference on double categories, so that makes sense. And but in this talk, I want to focus on how kind of we look at double categories from different perspectives, from different, like we use different equivalences when we work with them. And a priori, set theory cannot capture this notion, and how a different kind of perspective on double category theory can mitigate the situation. So that's kind of the overarching goal. And before I go there, I want to kind of spend a significant amount of time going through examples of how double categories, although they technically have the same definition, manifest very differently. And we think of them very differently based on which examples we are looking at. And I want to look at three examples coming from two limit theory, from two types of embeddings, from two categories to double categories. Okay, let me start with the first example. And for this first example, let me just review quickly or / introduce, depending on who you are, two definitions. I use the word first and second underlying horizontal category. So the first underlying horizontal category, I think is very common, just called the underlying horizontal category, has objects, the objects of the double category, and morphisms are the horizontal morphisms. But I will also use the word second underlying horizontal category for the one where the objects are the vertical morphisms and the morphisms are the squares. So just to simplify notation and language, just like terminology I use for this talk. Okay, so now what I can define is a notion of a horizontally terminal object. It's also called terminal, but I want to make clear that there's a directionality here. And it's an object in a double category, which is terminal in the underlying horizontal category, and a vertical identity on the object is terminal in the second underlying horizontal category. So let's see how this kind of manifests and what this has to do with two limits. So I will now fix a two functor f from I to c and L some object in C. Yeah, not mentioned, but L is an object. Yeah. And so what I can do now is I can construct the following double category, which looks like this. So I am not describing the composition and so on, but I'm giving you the objects. So these are the here are the objects. These are the horizontal morphisms, the vertical morphisms, and the squares. And well, here the objects are just cones, so that's why it's called the double category of cones, from an arbitrary object into the diagram F. Morphisms are just morphism of cones. The vertical morphisms are two morphisms into cones, and then the squares are what they have to be to make things work. And I can similarly construct something for a given object. So here again, the same. Here I have the objects, the horizontal morphisms, vertical, and squares. And well, what is a two limit? In a two limit, what I need to know is that a morphism of cones here should okay. The morphism of cones should correspond precisely to a morphism of objects, and a two morphism in the cone should correspond to a two morphism of objects. Moreover, I know that this one has a terminal object, a horizontally terminal object, given by identity. Very, very standard. So if I put all of this together, an equivalence between these double categories and terminality should have something to do with two limits. And as a matter of fact, this is a real theorem, I'm not just making up. And it says that if I have a two functor, I can observe that f has a two limit if and only if there's an equivalence between this slice over L, this double category, and the double category cones, if and only if f has this C over f has a horizontally terminal object. But the key question now one has to ask is what we mean by equivalence. What kind of equivalence will make things work? And if you go back to the diagram, what I should know is that in some sense, this category should be equivalent to this one, and this category exactly should be equivalent to this one. That's kind of how the terminal objects interact. They live in each row separately. And so that's what we can give a name, and we can say we have a horizontal equivalence of double categories if a double functor induces an equivalence on the first and second underlying horizontal categories. And now it's not that difficult to prove that if you have two double categories that are horizontally equivalent, then one has a terminal object if one if the other one is. Because terminal objects are preserved and reflected by equivalence of categories. So when we're working with double categories that come from a theory of two limits, the right notion of equivalence that works for us are exactly these horizontal equivalences. Of course, the point of this talk is that this will not generalize. So another thing that we can do is we can embed two categories and double categories. As a matter of fact, people often say that, like a two category is just a double category with trivial vertical morphisms or something like this. And that means there's a very precise, fully favorable functor from two categories to double categories. And yeah, so in general, it kind of looks like this diagram, where the vertical morphisms are just the same as the objects. And now we can ask ourselves, is it true that if two categories are equivalent to each other, are bi-equivalent, then the resulting double categories are equivalent? And here, this will not be true if we use horizontal equivalence. Of course, for example, if you look at the free adjoint equivalence, so adject here denotes the true category that classifies the adjoint equivalence shape, then the underlying category of this is definitely not equivalent to the terminal category. Just not true. It has, and as a matter of fact, every morphism has inverse, but up to some two isomorphism, not strictly. So it is not true that this, as a double category, this adject will not be horizontally equivalent to the terminal object. What we need is something that takes all the two categorical structure into account. And there are, I think, more than one ways of doing this. But one way that works is to kind of generalize from a horizontal equivalence to what I call a horizontal bioequivalence. And so horizontal bioequivalence is an induced bioequivalence on the first and second underlying two categories. Now, I have not defined those terms, so it's not a definition in any real sense of the word. But I have given you a citation. So if you're interested, you can look it up. There's a very precise definition how we can extract two kind of horizontal two categories out of a double category. And in this case, it will really be true that bioequivalent two categories induce horizontally bioequivalent double categories. So in that context, these horizontal bioequivalences are the natural notion to consider. Going one last example, we can have a second embedding from two categories into bicategories, which instead of just embedding trivially on the vertical morphism, we just repeat the same one morphisms. And then our squares are just like squares. So yes. And this is called a square functor. It plays apparently an important role in things related to geometry, which I know nothing about. But if you just take it on faith that this is a functor that exists, the next question we can ask ourselves is, what kind of equivalence do we want to look at here? And the first thing we notice about this functor, which is very different from all the previous examples, is that this is nicely symmetric. So if I put a line here in between, and I flip it around, nothing changes. So the first naive intuition would be that whatever notion of equivalence one wants here should have the property that if you flip the notion of equivalence around, it's also nicely invariant. And this is not the case for the horizontal equivalence or biequivalence. Like the word horizontal suggests there's like a directionality to them, which is useful for their purposes, but not exactly what you want here. And there's like a third notional equivalence that one can consider, which is called a gregarious equivalence. And unfortunately, defining it precisely involves some amount of slides, so I will skip it. But there's a certain equivalence relation here that one uses that needs for objects that involves kind of like companions and so on. But I promise you this equivalence relation is symmetric. So if you're willing to believe this, then a gregarious equivalence is any functor that is surjective on objects up to this symmetric equivalence relation, is surjective on horizontal and vertical morphisms up to two isomorphisms, and bijective on squares. And here exactly, I'm doing the same condition on horizontal and vertical morphisms, so it's indeed symmetric in both. And then it is in fact true that if I have biequivalent two categories and apply the square functor, then the resulting thing will be gregariously equivalent. So this, I'm citing this paper, but it's not literally written in this form, but it's more or less there. So if you want to ask more about this, feel free to comment on this. But this result is definitely true, and it's more or less in this paper that I cited. So up until now, we have seen three different types of double categories. So double categories of cones, like the kind of embedding where the vertical morphisms are trivial and embedding via squares. And for each one, technically they're all the same. Like they're all double categories. They all have the same definition. But we all think of them very differently because when we look at them, we can tell what is the information that matters and what kind of equivalences make sense. And that's kind of annoying, right? There's no way to build the equivalence into the definition. And so I think a legitimate question would be, okay, but like, wasn't this the same for one categories or two categories? I mean, they also have different equivalences. And you never complained about this. So the first answer is I did, you just didn't know. And the second answer is for the 1 and 2 categories, we do have the benefit that there is some sort of linearity. Like there's at least one notion of equivalence that is like weaker than all the others. And this at least gives me a sense that, okay, if I don't know, I just start with the weakest one. And maybe I strictify to the one that I need to. In the context of double categories, I'm not trying to be like super exhaustive, but I just like put some naive list together of like, so I take iso, here's the free isomorphism, so just the walking iso, adject we already mentioned, is the free adjoint equivalence, and I can embed it in double categories in like 3 different ways, using the horizontal embedding, vertical embedding, or the square embedding. And then I can ask myself, is it contractible according to these like 5 equivalences that I stated? And in some it is, in some it isn't. So tick means it is, X no. And there's no one equivalence that will like cover all the others. That's someone like strictly weaker than all the others or strictly stronger. It's somewhat in between. There's like, depending on what you're doing, some equivalence is better or worse. So like double categories are just like much more diverse in that sense. Like, there's much more kind of different equivalences that we can consider. And that kind of fits well into this conference, right? We're looking at double categories and like there's lots of speakers, but also lots of perspectives. I'm like, okay, what am I using them for, right? With different angles. So with that, double categories come with a lot of equivalences. Let me make one comment here. It's something I completely ignored until now, and I will mostly ignore for this talk, is I worked only with strict double categories. But for many examples, we actually weaken our structure even, and that creates additional problems and additional kind of technicalities. So we can in fact look at so-called pseudo double categories, where like the composition in the horizontal direction is, for example, strict, but the vertical one is weak, and then we need additional data to specify it. Or we can look at the so-called doubly weak double categories, where both compositions are weak. And for those, we have additionally choices of kind of equivalences that come up that make sense and that we use to compare. For that reason, I just keep it technically simpler. In these examples, I focus just on strict ones, but there actually are additional examples coming from there. And so, yeah, things get even more complicated from here. And we can define these kind of like weakenings categorical sense in the set-theoretical setting, but like we cannot capture the equivalences the way we want. All right. And with that, let me take like 20 seconds and have a break. And apparently you're allowed to ask questions in the chat. So if there's questions, feel free to ask. If not, I will move on. Because this is the example portion, and now I want to move on to actual like more like definitions.
There aren't any questions in the chat at the moment.
Good. I mean, I hope. I mean, the first part was mostly examples. So I think in a double category conference, most of it was very, very familiar to like everybody, which was the whole point. Like I want to say stuff that everybody knew to get convinced that this makes sense. Okay, so we all believe that double categories are cool, but they're complicated, and that set theory cannot capture all the equivalences. So what's the solution? A different foundation. Let's try that. And so now I want to kind of spend some time explaining what I mean by a different foundation, because this is the part that I will not assume at all anybody is familiar with, but some might be, but I assume nobody else. Most people aren't. Okay, so the thing that I want to use is what's called type theory. And so I broke up type theory into 3 steps. And I start with the part that makes sense from somebody who has not done type theory. And so here's the slogan that like Mike Schulman told me like around 10 years ago. It's not a definition, but it's kind of instructive. It's like type theory is doing category theory and zooming in so much that one forgets that one was in a category in the first place. One is in between the objects and morphisms and doesn't see the external layer of categories in. So this is kind of how type theory works. Okay, there's not a definition. Don't quote me on this. Just maybe as a heuristic. And more precisely, so type theory consists of types. So there's various types. There's terms. Each term has a type. And there's type constructors. And the analogy is a type is kind of like a set or like an object in a category. The terms are kind of like the elements, right, which live in sets. Or in the context of category, it would be kind of like morphisms that have a specific domain. And the type constructors are various things I can do with types to put it together. And so like set constructions. In category theory, is more like the various universal properties, colimits, limits, and so on. Just to clarify, type theory often in people's minds have something to do with computers. They don't have to. In fact, type theory goes back to at least 1908. So it's way, way before computers. You can a priori just use it as a foundation. So there is some connection to computers, true, but it doesn't have to be. And in this talk, it won't. So we can start with some type constructors, the way we do set theory. So there's a one element set, there's a unit type. The unit type has exactly one term, and any other term is equal to that one term. There's one term alone. There's an empty type, which has no terms. If I have two types, I can take the product. And a term in the product is a pair. This is very standard. There's a function type. So I don't know, unlike in like elementary set theory courses where functions are defined like relations with blah, functions here are just like a native type. There's a type of functions that from a domain to a codomain. We call it a function type. Okay, so those are similar. I mean, I didn't mention all of it, but similar to coproduct, there's also like some kind of like sum type and so on. There's a bunch of types similar to the one in set theory, but I want to move to the one that are slightly more complicated. And one thing I want to do is I want to have a type of all types, and I want to be able to talk about type depending on something else. So like a so-called dependent type. And for that, I need to like get slightly more technical. Not too yet, but slightly. And the first thing I want is a universe type. So there's a type U, and a term in this type represents types. So it's like the set of all sets. Exactly that, more or less. Of course, like always, what I don't want to have is something like this. I don't want to be able to say U in U. This looks weird, right? And so in similar to like in set theory, you have Russell's paradox. You cannot have the set of all sets literally, because then the set would be an element in itself, and then you have problems. There are solutions via hierarchies and so on. I will completely ignore this for the purpose of this talk. I'll just assume there's some type of types, whatever. Right? It suffices. But yes, the paradox needs to be dealt with if you want to do precise math, whatever. Okay, so now that I have a universe, what should be a dependent type? I will just think of a dependent type as a function type into the universe. So thinking from a set theoretical perspective, dependent type is just a collection of sets, a set index collection of sets, where like the collection depends on the index set. That's basically what it is. So up to you here, nothing crazy. But now I can do cooler things. Now that I have this dependent types, I can do like more advanced type constructors. Namely, what I can do is a so-called sigma type. And so what I can do is a sigma type is like a fancy version of a product. And instead of just having pairs, elements like A and B, I have an element A. And then here this X will be in some type BA, where B depends on A. And so this is exactly where I use the dependence, right? So example is in the context of sets, I'm just taking the disjoint union of this index set over exactly the indexing and to put them all together. So if this was constant, it would just be the product of A and B. But if it's not constant, it's just a disjoint union of all these kind of index sets I've collected. I can also take a look and think of this from a groupoidal perspective. If I think of, so here, if in the context of groupoids, let me just note. So if I say B is an A-index collection of groupoids, what I mean is B is a functor from A to groupoid. Where here groupoid is the groupoid of groupoids, the universe. A is a groupoid, it's a functor. And now I want some collection over A that bundles all the information. And the standard thing I do in category theory is a data-grid deconstruction, which kind of lives very nicely over A. And the fiber over every point is precisely the value of B. So that's exactly how this all fits together. So the first thing I can do is I can do a sigma type, which, well, yeah, like I said, it's like some kind of like bundling of the dependent type, and I can take pi types. And the pi type is like an analog of a function type, but here again, a term in this function type takes an A, not to something arbitrary, but something in BA. So I'm changing the codomain of my function based on the input. And the set-theoretical way of thinking it is exactly a section. Because if I want to construct a section here, what I need to do is I need to take an element A to something that is precisely in a fiber over A in order to be a section. So I'm changing the codomains according to the input that I'm starting with. All right, so why did I say all of this? Because now I want to get to the really confusing part. Namely, in type theory, the weird thing and the useful thing is that there's nothing outside of it. And what do I mean by the words there's nothing outside of it? I mean that the logic or all the sentences, the formulas and so on, they don't live outside of type theory, they live inside of the type theory. So I need to, in particular, internalize every single kind of mathematical symbol I use to say anything about math into my type theory. So let me start with like identity. So now my identity itself is a type. So now this thing is literally a type in the type theory. It's not like a symbol. It's not like some kind of sentence or formula. It's a type inside of it. It depends on x times x because we have two free variables, x and y here in this case. And well, it has various properties that are important. And so in particular, the property then is that if, for example, if I take the same element, if I take the same kind of terms, x and x, then I do know that there exists a term. So I know everything is equal to itself. That's kind of like convention. Then in some sense, I say that two terms are equal if exactly this type has a term. So if I can find something in the term of the type of equalities, then I say it's equal. And for types themselves, I know every type is a term in the universe. So being equal just means this equality has a term. Okay, so it seems similar, but again, the key thing is that a priori, this type, this thing, equality, is itself a type in the universe. Is a type like in the type theory. So it's not something outside of it. So for example, let me look at two examples. If I'm in the world of sets, fixed as a set, then my dependent type should be something like, well, from S times S in the set. And what I want is I want to exactly have the property that if I have two elements and if they're equal, then indeed there's some witness that is equality. If they're not equal, there's nothing. So I just define like this kind of like diagonal map, right? Which like takes an SNT to like this delta ST in some sense. So it's a point, if they're equal, empty otherwise. And if I take the sigma type of this, then I exactly get diagonal maps sitting over S times S. Right? If I bundle all of this information, I get this. Another example, if I'm in groupoids, then what should it mean for two terms to be equal in a groupoid? Should be that they're isomorphic, like there's an isomorphism between them. So the equality is exactly the isomorphisms from G to H. But in a groupoid, the isomorphisms are precisely the morphisms. Right? Because every morphism is isomorphism. So it's literally just Hom GH. And if I now put all this together, bundle it, I get the path groupoid. I get the groupoid of arrows exactly sitting. So here, recall, this is not dependent. So this is sitting over G times G. Exactly. So again, like the identity now is a groupoid in some sense. In this case, the groupoid is discrete, right? So Hom GH, you might say, okay, wait, if I have a groupoid, this is a set. This is completely correct. But it's still a discrete groupoid. It's a groupoid when there's no isomorphism. There's a question, wait, is the equality between these types in the example then an identity type in U? Yes. There's a type in U. Identity type. I don't know what identity type in U means. It's a type in U. I think that's the question. If I understood it correctly, I want to say. Yes, the type of identities is a type in U. Okay, good. Yeah, fine. All right. So this is the first thing, equality. Another thing that's very important are quantifiers. So when we do actual math, we consistently use for all and exists to do stuff. So here's an exercise. I will not solve it. If you get bored by the rest of the talk, feel free to work on it. Namely, whenever I have a set S, and I have a formula, phi x, where x is an S, then I can form this set. namely the set of all elements in X for which phi x is true. And now the exercise is there exists an X and S phi x if and only if this set is non-empty, and for all X and S phi x if and only if the obvious map to S has a section. This is the simple exercise you can try out. Now, why did I say this? Of course, we just had seen like some total space and some section before. So now what I can do is I can say a term in a dependent. So if I think of a dependent type as a formula, so if I have kind of like if I now think of phi like this as a dependent type S into U, where U is something like a global thing, then having a term in the sigma type is some sort of existential statement. Having a term in the pi type is some sort of a universal statement. And so this is how I put both kind of constructors and logic into one framework altogether at the same time. And then I have to recognize how I'm using this based on what I want to do. So we can then summarize this type theory stuff in some sort of table like this, where, so like I said, we mentioned the unit type. The unit type is like the singleton element, but from a logic perspective, it's just true because it has a term. So things that have terms are the true things. The empty type has nothing, so it's false. Product is kind of like and. Function types is exactly implies. This is also kind of really important. We use it a lot. That we want to kind of prove something implies something. We construct a function from the domain, the thing that we have, to the thing that we want. And then, yeah, so sigma and pi types are exactly exists and for all. All right. Now, this is just like the basics of type theory. Up until now, I've not used the word univalent or anything like this. But let me like give you one example and then get to that. So let me give you like one very crude example of how you can use type theory to prove stuff, which is like too easy, but like I think brings the example maybe as a useful kind of heuristic at least. So I can define now what I call a magma. So a magma is again, in classical math, just a set along with an operation, like so nothing else. In type theory, now I can just say, okay, what should it be? I should have a pair X and a map from X times X to X. Very nice. How do I construct pairs? We mentioned this, sigma types. So I just write a sigma of an X and U and a product. What is an associative magma? It's exactly this, plus, and here now in set theory, we would write this as a sentence plus like, I don't know, for all, blah, blah, blah. But in this case, we don't have a for all, blah, blah, blah anymore. We just put this into the data and then use the pi type, which replaces our universal quantifier. So now there's one type here, this one type, that a term in this is precisely data of X, M, and something that witnesses the fact that it's associative. So there's something, like a term here would be like X, M, A, like a triple like this, where A is exactly a function which has input X, Y, Z, and the output is precisely identity between these like two different terms. And now I can like start proving things like every associative magma is a magma. And what's the proof? We mentioned when we want to induce something, we construct a function. I need to construct a function from associative magmas to magmas, and there's one obvious one, pi one. Notice if you could construct any other function, this statement would also be proven. Any term in this type is a proof, but I don't know if one could do that in this case. But there's actually nothing pre-given. You just need a term. So that's how you then start doing math. You have these functions, you have these pi and sigma types, and you start constructing terms in them. And construct a term in them means you're proving a statement and you move on. Okay, so now we want to move on and see how univalence comes into this. And the key question about univalence is, how does your identity type behave? And one version of the identity type is that it has the so-called uniqueness of identity proofs, which means that whenever you have two different terms that live in this identity, then they're equal. In other words, X, in like more or less, one can say, it's not very precise, is empty or contractible. Empty or unit. This is kind of how we live, how set theory works, right? It's two things are either equal or they're not. And there's no like third option or like other options or so on. We kind of like restrict it. And that's how you can do like type theory. It's totally reasonable. There's nothing wrong with that. But you don't get much out of this identity type. It doesn't have any expressive power beyond two things are equal or not. The other version is to like give it some extra structure. And for that, we first review a notion of equivalence. So there's a type of equivalences which roughly is what you think it is. It's like the data of, so it's like the data of a function f and two inverses g and h that compose the identity. So in the context of sets, this would be just the isomorphisms, but a groupoids gives you back equivalences. And now you can ask yourself, do I have equivalences? And it turns out whenever two things are equal, they're also equivalent. Any equality gives you an equivalence. It's not too tricky. But now the question is the opposite true? Can you get an identity out of an equivalence? This is generally not true, or there's no way to prove it or disprove it. And so you can make it into an axiom, the so-called univalent axiom, and assume that this is true in the definition. So now whenever I have an equivalence between two types constructed, I can deduce that this gives me an identity. And so now I can use this to do kind of like cool things. And I can kind of start giving my type theory some sort of topological or homotopical flavor. So for example, I can now state what it means to be a set. And here the word set is slightly unfortunate because it's not literally set in the set theory sense. It's just saying that it's like zero truncated. So it has this kind of property. And sets do have this property. So we call it set in like univalent type theory. But yeah, I don't know. This is a little bit of an unfortunate like naming for people who have never worked with this. But this is saying that, well, exactly, if I have two types this is saying exactly that it has this so-called UIP property. But now I know that this is not always true. So for some types, it will still be true that they have this property, that any identity is equal. But in general, this will not be true. We can have many times where this fails, and we'll see examples of that. And so, but I can now start kind of bringing homotopical ideas into it. Another important thing I can do, this is really what we care about for this talk also, is that now the identities in the universe have a lot of extra information that kind of captures the data that I want. So for example, I talked about, okay, let's uni be univalent. So it has this property that if they are equivalent, they are equal. Then identities in U correspond to equivalences, this is by definition. But now it's also true that if I look at MAC, so MAC was defined by a type and like its operation. And an identity will precisely be an equivalence that respects the operation. An equivalence of types that exactly preserves the operation. There's a somewhat controversial take in the chat that people can read and decide whether they agree or not. But it's an interesting take, I shall say, for this talk. And similarly, asorgmark, so the type of associative magmas is exactly the identity is exactly an equivalence that respects the operation and the associativity. So the equivalence, the identity adapts with the type. It changes because it was defined internally. This is very, very different from set theory, right? If I define a group, identities don't automatically change and become like isomorphisms or homomorphisms or anything like this, right? Identity is external to the theory. It just is what it is. And you have to kind of then explicitly say, okay, I want an isomorphism. Here, this is not the case. The identity is in the theory. And when I define stuff, the identity changes along with it. It's kind of cool. So let's look at some examples of univalence. In the context of sets, if I just think of sets as like a type, then the equivalence, type of equivalences is the set of isomorphisms. A equals B is a set of equalities, which is just empty or a point. So if you just unwind this, you see you have only univalence if A and B are empty or a point. There's just nothing else. Because as soon as you have two elements, there's a non-trivial isomorphism between them, like a flip, and this will not be captured by the equality anymore, for example. What else? So if I look at groupoids, in groupoids I can do better. I can take any discrete groupoid, and that's exactly the sets. So if I think of groupoids as on a type theory, the ones that are the sets are the ones that are discrete. And for those, I will have that the groupoid of equivalences coincides with the set of isomorphisms of the groupoid. So in some sense, the problem is when I'm working with like sets or groupoids, there's always like, I always have to go one dimension down to get some kind of univalence property. And so I need a number n for which n minus 1 is equal to n. And the solution to this is infinity. Right? If I go n equals infinity, infinity minus 1 is infinity, so it's good. So I need like a theory of infinity groupoids also. So I will like say quickly something about this, but I'm not assuming any kind of knowledge of infinity groupoids, and it doesn't matter for this talk, just as an example, like infinity groupoids or Kahn complexes or whatever homotopy types or whatever, if you know any of these words, are a precise model for this univalent type theory. where kind of just most of the constructors work the way we explained. Just you mentioned dependent types kind of correspond to count vibrations, and I get exactly an identity type as like a path vibration, which is kind of similar to how I got for group weights. And in this case, it's kind of nice to see that n truncatedness corresponds exactly as it should. So a zero truncated homotopy type is exactly a zero truncated type in the hot sense. They're exactly the same. And my identity types are equivalences, like equivalences of homotypes in the homotopical sense. So there's a very precise way of doing this. We will not need it. I'm not doing infinite category stuff for this talk. Okay, to summarize, type theory is a language for doing math. It has something to do with computers sometimes. It doesn't have to. Type theory internalizes its own language. This is really important. It has a notion of identity that comes into it. Notion of for all exists. All of it is in the type theory. The identity can be more or less trivial, but it comes to be very complicated. And we want to use this stronger identity to now do cool double category stuff. All right. And with that, let's take a second quick break and move to the last part of the talk. So I didn't know which type of KitKat people liked, so I mixed it up. No questions? Then I just give you like a 10-second break to maybe wake up, and we shall continue then. Okay, so here's a definition of a category in type theories. It's very simple, super easy, nothing special. I mean, indeed, it's now, hopefully, with some of the terminology I've gotten into, this is not too crazy. So what is a category? It's objects, morphisms, composition, identity, and so on. So it's a gigantic tuple with data. Tuples in type theory are with sigma. And then I just start doing it. I say object, it's just a type of objects, type of morphisms, composition. And then whenever I have these axioms, I need to say for all, blah, blah, blah. So I have all these pi types here. Just say like for all objects x, y, z, for example, I have a composition operation and so on. The only thing I point out, I really want a category. So I want a set of objects. So there's this one additional term that one might not be used to, that I have a hom set, so I have a set of morphisms. I am not making any assumptions on the objects right now. I'm just assuming that the morphisms form a set. Okay, so now the question is, what is the identity of categories? So now, just to be clear, so cat is now a type. And a term in this type is like a tuple with all this information and can extract the data I want from this tuple the way I need to. What does it mean to be equal? So if I have C equal D, and so here there should be a subscript cat. And if I just unwind the definition of identity using the axioms of identity in type theory, it is exactly a term, an identity between the two objects and an identity between the morphisms, and it has respect to structure, so the composition, identity, and so on. So that's appropriately functorial. This one, if you think about it, we agreed that these two are sets, and we know that identities of sets are exactly the bijections. So true always just means it's fully faithful, just a bijection of sets. So I forgot to mention, I'm doing first a prelude on categories because categories are much simpler, and then I want to move on double categories. So not that you complain why I'm talking about categories in a double category conference. I think categories are just easier to understand. Yeah, so this true is kind of reasonably easy to follow. It's exactly saying that there's a bijection between the hom sets and that respects the structure, so it's exactly the information being fully faithful. One is just saying that there's an equivalence of types of objects. This a priori means nothing. It means neither isomorphism nor does it mean equivalence. The question we can ask ourselves, what conditions should we impose on the categories so that it exactly means isomorphism of categories? And here the two observations that we make that are very standard is that an isomorphism is just fully faithful in a bijection on objects, and equivalence of sets correspond to bijections in the type theory, right? So this is in the type theory statement. And the first one is just, I guess, definition of isomorphism. So what we want is we want to additionally assume that the objects form a set. And so now we can actually use this as a definition and define a set category as a category with an object with this is wrong. Here, this is wrong. With a set of objects. Yes, I don't know why that happened. Sorry. Okay, the type constructor is correct. The description was wrong. Okay. Yeah, so it's exactly the type of categories where I also know that the objects are a set. And in this case, it is in fact true that the identities of set categories are precisely isomorphic. Okay, so this is like the first easy example. Now, making it slightly more complicated, when do I know that a functor is an equivalence? And here, this is also like a fun exercise. If you're like just doing category theory recently started, give it a try. F is an equivalence in any of the standard sense of the word equivalence. If it is fully faithful and an equivalence of underlying group weights. Give it a try. It's a fun exercise. And so what we want then is we want the identity of objects to correspond to equivalence of underlying group weights. So what we then want is define a type of category, which we also call univalent. So it's slightly confusing. This is different from being a univalent type theory. Like they chose the same word because they look similar, but it's not the same definition. So now I'm giving a property to my category. I'm saying it's univalent. And it's univalent if it is true that identities in the type of objects corresponds to equivalences in the category. And for those, it is in fact true that univalent categories, the identities correspond to equivalences. And this, if you know about high category theory and so on, this of course borrows heavily from ideas of Rasekh, so completeness. This I know the secretly is complete single space business, but one can kind of like use it explicitly for categories here. But it comes originally kind of from this stuff on high category theory. Okay, and so we can have a set category, a univalent category. We can construct now the type of those, and we know that the identities are exactly the equivalences we want. Okay, so for categories, it's not that exciting because there are only two, so it's reasonably manageable. What we want is for double categories. So I'm not going to write an explicit definition of a double category using sigma and pi types because that would be like 25 slides. And then my time would up, but you can imagine I can just start using sigma and pi types and all these kind of conditions of a double category and write it down. The essence is more or less, it is true that an identity between two double categories in the setting corresponds to an identity between the objects, and then identities between the horizontal, vertical morphisms and squares that kind of respect the original identities I started with. And everything has to be appropriately factored. And again, I want to assume that squares form a set, like the highest layer. So this one is some sort of fully faithfulness condition. But the other ones are a priori unclear, and we have to kind of like choose how we do things. And the first thing we can ask ourselves is, okay, under which condition will this just be an isomorphism of double categories? That's the easy one. Everything should be a set, then we're good. So a double set category is a double category where everything is a set. And then it is in fact true that identities of those correspond to isomorphisms. That's always a standard one. But everything you define, if you make everything a set, you just get back to isomorphisms. That's fine. But of course, we want to go for more interesting equivalences. And the one I want to focus on right now are horizontal equivalences, which remember, so horizontal equivalence is I have an equivalence on the underlying first and second horizontal categories. And the thing that should come out of this is that the thing that should make this work is they should be univalent, right? So I should have, if I draw it, I have like objects, horizontal morphisms, vertical morphisms, squares. What should be true is that this row should be univalent and this row should be univalent, and then I should be good. Because then going back to the stuff before, a map between them, an identity between them will exactly be an equivalence. Cool. The problem is that if I make this assumption, then this category here of objects and vertical morphisms is neither a set category nor a univalent category. It cannot be either of those. So we in fact are forced in a type theory to relax the structure and work with so-called pseudo double categories, which have strict composition in one direction and weak composition in the other one. And so the upshot we get from this is that, okay, if we work with pseudo double categories, then we can exactly define it to be horizontally univalent if the first and second underlying horizontal categories are univalent. And then it is exactly true that identities correspond to horizontal equivalences in the way I defined. Okay. I will not continue giving you more and more examples because this will take forever. So now I will kind of just stop here and give you an overview of the kind of results you can get going from here. What you can do is you can like look at essentially now strict, pseudo, and weak kind of double categories, and then kind of choose a notion of equivalence that you want, and then construct in this type theory and the precise definition where the identities will correspond to the equivalence you want. And notice, for example, you get now interesting arrows here. So a full arrow means that in the type theory, you have an embedding. So it is true, for example, that you can embed strict double set categories and pseudo double set categories, because for them, both the identities are isomorphisms. But this one will not exist as an embedding. There will not be an embedding from pseudo double set categories to univalent ones. Because like, what is this saying? In the type theory, it would say that if two things are isomorphic, they're equivalent. And this is just if and only if they're equivalent, right? This is not true. Things can be equivalent without being isomorphic. It's like a weaker condition. And the lack of embedding from this top to the bottom is exactly capturing this information. So we can kind of now define various double categories in this setting that have the exact right notion of equivalence we want. And we also, so I didn't mention this, but there's also like this common kind of pre-double categorical structure that one can look at due to Verity, which is kind of double bi-category. And that also kind of has like a nice universe property and reacts well with gregarious equivalences that we look at. But the definition is like way too long to discuss here. So I completely skipped it. But if you want to talk about it, I'm happy to do that. All right. Let me then summarize what we did. So generally, categorical structure comes with many equivalences. And we can, if the equivalents are only one or two options, then whatever, you can ignore it. But the more complicated your category gets, so from category to double category, you get more types of equivalences, and you cannot capture that in the definition. So you either have to kind of use an intuitive sense of which equivalence is appropriate, or you have to kind of explicitly mention, I want double categories up to blah or up to this. And the alternative is to use a foundation where you can build the equivalence into the definition. You can exactly say, if I now say a univalent pseudo double category, I mean a pseudo double category, and the equivalence will be like horizontal equivalence, for example. This kind of makes the math you're using somewhat more precise. It allows you also like just to be more just easier. You're just giving names to things that you're thinking at sometimes. We do this for double categories. I did this for this talk because it's a conference on double categories. But you can also do this for true categories. So there's a similar one, and presumably for anything else that's similarly defined. And we call this kind of result the univalence maxim, that there's a relation between categories and a chosen equivalence, and a nice definition in the univalent setting that captures this. So there should be like some kind of abstract theory that makes this more precise, that is yet waiting to be figured out completely. Okay, how am I doing on time? Okay, it's 49. I have 1 more minute. So I had like 2 more slides talking a little bit about the connection to formalization. So I will skip this, but you can ask if you want. And with that, I will get to my last slide. And well, if you have any questions, you can ask me. You can also look at, so let me just mention one word. There is also, in fact, a formalization of a lot of the stuff we do using kind of, computers. I try to skip most of the computer stuff, but like I said, if you have questions about this, I'm happy to discuss. We have, I think, reasonable amount of time. And now, if you have, you can also check out the 2 papers on this. Yeah. And with that, thank you.
Okay, thank you very much, Nima, for the talk. Thank you. I will let people unmute themselves. So if you have a question now, you can either type it into the chat, you can raise your hand, you can unmute yourself, or I think those are the only 2 options. So there's a question in the chat.
Okay.
I will just read out for the recording, which is on slide 52, why is the lowest left inclusion not dotted?
So, well, this is so I did not explain the definition. This is a cool fact, right? So I can have 2 double categories up to horizontal equivalence. And I can have like weak double up to gregarious, and I cannot embed one in the other, which makes sense. I'm changing the equivalences. But this funny thing is this notion of double bi-category, very double bi-category, is not a double category. It's like there's a double category with extra information. So there's additional kind of explicit 2 cells in the definition. And that allows you to kind of make two separate different, like there's no commutation here. There's two different embeddings from pseudo-double categories and weak ones, where both of them preserve univalence. But I've not told you what the embeddings are, so the sentence does not make as much sense as it should. Yeah, it's a good point.
Thanks. And then Nathaniel, feel free to unmute yourself.
Hi, Nima. Thanks for the talk.
Hello.
In many respects, virtual double categories are more nicely behaved than pseudo double categories. I was wondering whether you'd studied the appropriate notion of isomorphism or equivalence here.
I think I need more convincing on the sentence, the first sentence.
Well, for instance, like the two category of virtual double categories is complete and co-complete, but this isn't true for, say, the two category of pseudo double categories and pseudo or lax functors, for instance. So two categorically is much better behaved, and there are various other reasons why, but that's one example.
So okay, the quick answer is we have not. Just because I have a hard time working with virtual double categories, I should ask you. So then maybe I send you an email and you can tell me more about this. This is interesting. I mean, I do have like my just questions about virtual double categories. I just like, yeah, we have not worked on this. I think a priori there's no reason you couldn't. There's just no like foundational reason that you couldn't work on them. But just like maybe just time, like we are focused on the thing that, I don't know, the examples that we kind of, so one of the things that I was really interested in, of course, I don't know, so there's the stuff about limits and so on, that like, so there's stuff that I've been doing on this for a while. That's kind of interested. And there, the thing that matters is really these like horizontal equivalences of pseudo double categories that can naturally come up. But yeah, you should tell me more about this, I think. It's interesting.
Thanks, yeah. Be happy to hear from you.
Hi, sorry, I have a question. You said the issue, why there are the dotted arrows? Is it because you don't have this strict hierarchy of equivalences? So does that mean that if you're working with the bicategorical setting, you would have all these strict, you would have all these non-dotted arrows in their between their corresponding type theories, or am I misinterpreting this?
I don't follow the question really.
So
What's the context? Can you repeat this?
Yeah, okay. So you said the difference between double categories and these bicategories and their equivalences is that you have a strict hierarchy.
Double categories, and you mean like double bicategories here?
No, I just mean real bicategories.
Bicategories. Okay, so double categories and bicategories.
Yes.
Okay.
And in the beginning you said, well, you have for bicategories this strict hierarchy from
Yes. Okay,
isomorphisms to equivalences and lower. Does that imply then that when you start doing their type theories, where you can interpret these equivalences as the right identities to these respective type theories, do you then got full arrows?
No, you have the same issue. You get, I mean,
okay.
Yeah, but this is, I mean, so here, where is it? The panel, but it applies to any other category, so just two categories. And this is true. I mean, you have the same thing. You can define like a biset category. So it's a bicategory up to isomorphism. And you can define a univalent bicategory, which is a bicategory up to biequivalence.
Yeah.
And it will not be true that the first embeds in the second, right? Because again, for the same reason. So you don't have you have separate notions. Similarly, all I was trying to say is that on a very like just intuitive level, when people talk, the fact that there's a one weakest equivalence makes it easier just to start at that weakest one, and then maybe if need be, like maybe say, okay, but I want this equivalence, which is like somewhat stronger than this.
Yeah.
Just as an intuitive level. In a type theory, there's all of these, like any equivalence will give you a different definition. They're not the same.
Okay.
Yeah, you have the same exact, you have the same every diagram. There's a diagram, I didn't include it in this talk. Like I said, I focused on the double category stuff.
Yeah.
But like in this paper, there's in fact a diagram for two categories too in the second one.
Okay, perfect. Thanks.
Yeah.
Just a comment. When you have those dotted arrows, they end up being kind of like a res completion.
Well, there should be. It's not all of them are, but there should be some sort of rest completion if you want. That's a good like a conjectural way. The problem is, I mean, you have to be able to construct the rest completion if you want, and just like this is not the standard way. I think, or one common way of doing rest completion is some sort of like UNITA embedding, right? That's an example of like this is the kind of trick you use. The problem is UNITA embeddings and double category theory are not that easy, because like double categories are kind of like the enrichments are trickier. But yeah, conjecturally, I think this is a reasonable way of looking at it. I mean, I just meant it as classically there is a function, but in a type theory there won't be. But I think there should be in a type theory something of completion.
If there's no other questions, maybe this is risky, but could you spend 45 seconds going through the two formalization slides, maybe?
45. Okay, let's do this. Okay, so formalization is something that like some people do. It involves taking like a math statement, and then you make it into a type theory, which we have now seen. So you write down a type theory statement. And turns out that these like programming languages, so-called like functional programming languages, which are kind of designed to input these type theory statements with sigma and pi and whatnot, and make like programming stuff, right? And then there's a way that computers can like formally check if this programming language written is correct or not. So you can like write definitions, but also theorems and lemmas and so on. It has become more relevant recently because like math is harder and computers are better than they used to. And like two examples are like common. There's this so-called liquid tensor experiment that was done in Lean. There's also like a lot of like univalent mathematics and topology and so on done in, let's say, Coq or Agda and so on. So there's now formalization growing. One funny fact is that we use a lot in math. Like here's a common thing that we use a lot in the proof lemma. The bicategory A has this property. Proof from blah, we know that A is equivalent to B, and from blah, we know that B has this property. This is a very common proof. If you try to do this in a computer, the computer will like viciously yell at you, because just being equivalent is not enough to transfer property from one side to the other. There's there's transport properties where are you allowed to transport a term, i.e. like a witness for something from one place to another. And univalence allows you to actually do this, because for univalence you get equivalence as identity, and when two things are equal, then you can do this. So when you try to work with kind of double categories and bicategories in this formalization setting, it's very, very beneficial to be able to use this kind of univalence, where you can kind of reduce everything to identities and like reduce proofs, right? So, and this is kind of like one kind of big motivation in the formalization world, why you would care about these like identity principles, where you can kind of go from like one type of definition to another one. So it's more than 45 seconds, but not by much. So stop it here.
That was very efficient. Thank you very
Right.
much. And because it's 59 minutes past, thank Nima again for the talk. Thank you so much.